Good morning, everyone. Thank you for attending our webinar this morning. My name is David Dugagne. I'm a senior engineer with ITASCA in Minneapolis, responsible for technical marketing. We're very pleased to share with you this case study, which was conducted by ITASCA Chile. What we've done is pre-recorded the presentation, but at the end of the presentation, which is about 20 minutes long, we'll be happy to take questions. In Teams, you'll notice at the top of your screen, there is a Q&A icon. If you just click on that, you can type in a question and submit it, and then we will review those at the end. Today's presentation is presented by Patricio Gomez, who is the General Manager of ITASCA Chile. Catalina Alvarez will also be joining and available for questions.
Okay, thanks a lot, Dave. Welcome again, everyone, to this new webinar in the series on solving geotechnical challenges with ITASCA software. My name is Patricio Gomez, and I'm very excited to share with you some recent work we've done towards understanding the production drift behavior at Chuquicamata Underground Mine. So this time we will talk about a project carried out a few years ago jointly with CODELCO Chile and related to the block caving mine that has been developed below the Chuquicamata open pit in what is now called the Chuquicamata Underground Mine. What you will see today and hear today was already presented last September at the MASMIN 2024 conference in Kiruna, Sweden, and we want to acknowledge CODELCO for allowing this publication and also the two colleagues from CODELCO who collaborated in the study, Giuseppe Barindelli and Sixto Lopez. The head of the project on ITASCA's end and also presenter at the Kiruna conference was Catalina Alvarez. She has been with ITASCA for almost 20 years and will join us for the round of questions after the presentation is completed today. I will be sharing this presentation with you today. I am currently the General Manager for the South American operations of ITASCA. I have been with the company for over 30 years, and jointly with Catalina, we are the two senior principal consultants in geomechanics for the Chile office. Okay, so let's get started with the project background for you to understand the context of the work that was done. As you may all know, Chuquicamata is one of the world's largest open-pit copper mines, with operations dating back over a century, specifically to 1915. The underground phase began in 2019, targeting a central microblock which is located around 200 meters below the pit floor, as you can imagine from the image on the lower right side of the screen. For the first 10 months, production ran smoothly, although with some initial cracking of the shotcrete support. 10 months was the time it took for the cave to develop and start breaking through to the ground surface. By mid-2020, stability issues began surfacing on the drifts, including support failures and even collapses. Starting in February of that year, monthly observational monitoring had begun, classifying the damage levels as mild, moderate, or severe. These helped tracking the behavior of the support systems over time. Okay, from the geotechnical perspective, this slide is going to summarize all the basic components of the analysis. First of all, it's a porphyry deposit, as you may all know. There are mainly 3 units in the area of interest with good to fair rock mass quality. They are the potassic East porphyry, the sericitic East porphyry, and the quartzitic rock. There's also an area named the Americana Fault Zone, which is quite relevant on the right side of the polygon that we're going to be looking at. There's a number, approximately 16 subvertical faults that will be included in the analysis. There's also the well-known West Fault, which is a predominant regional feature that defines, in a way, the location of the ore body. And there's also, from the stress perspective, information about magnitudes of 15 megapascals for minor principal stress, 20 megapascals from the horizontal perspective, and there's also the notion that these are induced stresses due to the presence of the open pit, which at the time of the beginning of the project was in the order of 1,000 meters in depth. This slide presents some details of the mine plan for the first lift of the underground mine. The image on the left shows the general mine plan with the designation of the blocks and macro blocks. The one we focused in our study was the one named N1S1, or North 1, South 1, whose dimensions are shown in the center image. In this macro block, the mining advance goes from southwest to northeast, basically. The image on the right contains the distribution of geotechnical units at the elevation of the production level. Some of the subvertical faults in the area are also shown here. As we mentioned previously, starting in February of 2020, the mine started keeping an observational record of the support condition. The categories defined at the time were as follows. There's mild condition, where there's normal to slightly loaded support condition, as the images on the right show examples of that. There's the moderate condition, where the shotcut has open cracks and is considered a strongly loaded support condition. And finally, there's a severe condition, where the support is completely considered out of service. Let's now focus on the scope of work and the main challenges that we faced in this study. So regarding the objectives of the study, there were three very specific tasks. The first one really had to do with the conversion of the observational rating data into information that could be used for comparison with the modeling results. This was by far the most relevant and challenging part of the study because it implied connecting a modeling outcome in terms of strain, plasticity, degradation of the rock mass, etc., with field observations which were not quantitative but rather qualitative. The other two are pretty straightforward once the first one has been decided, and they are referred to the construction of the 3D model and the calibration itself. One of the main challenges that the team faced had to do with the source of the information. As you can see on the top right sketch, the observational information was captured mainly on a window of shotcreted rock, which was called the rock mass pillar. The presence of a concrete structure at the bottom of the drift walls has a practical effect of concealing the actual behavior of the rock mass, which only becomes apparent when the entire wall begins to mobilize. The color and photo scale in the bottom provides a good idea of the gradual degradation process that was recorded in the observational method. Here we show an example of the observational information transferred into plan views of the macro block drifts from month 18. As you can see, there's a reduced number of wide segments in the drifts and a rather high number of segments with either moderately or severely damaged support state. So if we can summarize the challenges faced in the study, they refer to the already mentioned comparison of qualitative observations versus quantitative numerical model results on one hand, and also to the need to study a specific portion of the rock mass volume, where the first macro block is developed. This led to implementing a stress transferring process from a mine scale stress model to a macro block scale stress model. While this is a well-known procedure, it requires careful definition of boundary conditions for the smaller model and a quality assurance of the stress transfer end result. Here's what we can mention regarding the role of ITASCA, the scope of work, and the technical details of the project. In a nutshell, our role was to provide the modeling expertise to conduct the analysis from model construction to interpretation of results. This also defined the scope of work as follows. Regarding the development of a 3D numerical model, both in conceptual and practical terms, two decisions were critical in the process. First of all is the selection of the appropriate tool for the analysis, and second, selecting the correct constitutive model for the interpretation of the material behavior. The actual calibration of the model is a trial and error process where we seek for the best match between observations and the digital twin. Here the team expertise is key in deciding what modeling result is close enough to the reality based on the available data and inherent limitations in rock mass characterization and monitoring. An implicit addition to the process described here was that as soon as the constitutive model was selected and it became clear what variable was going to be interpreted to try and match the field observations, we developed routines to simplify the numerical output, in some way mimicking the simplification inherent to the use of the rock mass pillar to interpret the overall pillar behavior. We will describe this simplification later on in this presentation. On the tool selection, it was quite clear from the beginning that the analysis needed to take into account the plastic behavior of the rock mass, as the pillars were exhibiting relevant deformations. This led immediately to consider Flag 3D as the tool of choice given its use of the mixed discretization technique. Then the question comes, what about the need to include geological structures? Isn't 3-deck better suited for that? The answer is, while 3-deck is well suited for easier representation of complex structures, the use of ITASCA's meshing tool, Griddle, allowed including the faults rather easily as well, giving us then a model capable of capturing all the necessary features of the volume of interest. On the constitutive model selection, it was clear, as it is in most yielding pillar analysis studies, that strain softening was a necessary feature, since the rock masses at Chuquicamata have been characterized using the Hooke-Brown envelope. IMASS, the ITASCA model for advanced strain softening, was selected. On the stress and deformation simulation itself, it is important to emphasize that the model is only able to capture damage due to the effect of abutment stresses, and that other operational aspects, like consequences of irregular drawing, for example, are not captured in the simulations. Here we can see a general description of the IMASS constitutive model. As you can see, it features a number of relevant mechanisms which allow robust capturing of the degradation of rock mass strength when subject to strain. The post-peak behavior is absolutely critical for capturing rock mass softening. A more brittle behavior will likely worsen the pillar drift stability. Epsilon crit is an input model parameter which is adjusted within the calibration process, particularly the K parameter. In practice, the IMASS model allows definition of 3 failure envelopes for a given rock mass: the peak envelope, the post-peak envelope, and the ultimate strength envelope or residual. By design, each envelope corresponds to stages defined in a known conceptual model for block caving, which is the origin of the IMASS model. The strength loss, or S-loss parameter, which emerges from the analysis, is used to correlate to damage categories. It varies between +1 and -1 and is another key parameter used in interpretation of the results. Let's now review the methodology that was used in the analysis. The flat 3D model was constructed with dimensions of approximately 700 meters on a side, and it has the following features. First of all, the pit geometry was kept for the 2019 condition. Second, as mentioned previously, the stress condition was imported from the mine scale model of the site. The drifts and drawbells were implicitly included in the analysis with 0.4 meter zone size and unsupported drifts. And also the 16 faults identified in the volume were included via the Griddle meshing tool. Here you can see a cross-section through the center of the macroblock with the relevant geotechnical units identified. Then, from the available seismic monitoring information, CODELCO determined that the cave advance has followed a more or less 1:8 ratio between the extracted and broken height, and this was the criterion used to represent the cave shape as time goes on. The image on the right shows an example cave geometry for month 12. It's worth noting that each time the cave is updated according to the extraction mine plan, the stresses in the broken material are reset to 0, allowing proper definition of the abutment stress condition. So let's review what was the outcome of the process. This image shows the abutment stresses developing around the cave for months 4, 8, and 12 in plain view at the top and in a cross-section at the bottom. Notice the stresses in between drifts in the lower image. It becomes evident that the most critical condition for the drifts occurred after the cave breakout to the surface. For the model drift behavior interpretation, 2 model emerging parameters were considered relevant: the maximum principal strain, as it represents the drift convergency, and the strength loss, as it represents the rock mass damage. Here we take a look at the variation of maximum principal strains in the upper row and S-loss parameter in the lower row for months 8, 12, and 20. If we highlight the drift collapses documented in month 20, several of those locations correspond to principal strains beyond 5% on the drifts, or loss values equal or less than 0.3. Notice on the left image that strength loss is normally and reasonably higher near the drift and lower at the center of the pillars. Therefore, the question arises on how much depth to consider as representative of the actual strength loss. In this regard, to facilitate the interpretation, rather than relating damage to a localized number of S-loss or strain like tunnel closure, it was decided calculating an average rock mass strength loss over each outer third of the pillars. This results in the interpretation shown on the right. Values estimated as representative for the three categories of damage were 0.65 and 0.3 based on the end results in month 20. Recall that zero damage means S-loss equals 1, with 0 being the post-peak residual, that is the maximum damage related to plastic strain. As mentioned previously, any calibration process is the best compromise between the information available and the interpretation of the variables of interest. In terms of the methodology, the representative damage category for each drift segment in the production level was assigned the highest damage between two nearby pillars. 120 segments were evaluated in each stage of mining advance. We highlight in the image some cases where this fits the observation and others where it doesn't. Let's look at the results now in a sort of time-lapse fashion. The image on the left will be showing the simplified strength loss interpretation from the model and the cave front position. The image on the right will show the percentage of segments in each category for each of the 8 drifts. A table at the top right of the image provides a comparison between model and observed percentages in each category. Notice that the observational model only began documenting the damage in approximately month 10, so for the first months we only have the model response. The reference to months is counted from the moment that extraction began. The first one is month number 4. If we look at month number 8, there's no field information either, but after 8 months there's a significant number of drift segments in moderate condition in the model already. When we go to month 12, now we have observational information. Remember that the cave breakthrough took place around month 10 or 12. So by comparing with the mine records, the model seems to be overestimating the severe category and underestimating the moderate category, but the mild category is quite accurate. Month 14, the severe category is still overrepresented, but is compensated again with the moderate damage. This is now month 16, and collapses appear in the stress shadow. Those on the west end don't seem to be related to the mine front, hence we suggested that they were likely caused by irregular drawing. That means that stagnant sectors in the cave will accumulate stresses which will overload the pillars. This is now month 18, and the overall damage categories match well with the observations, although the damage locations are not always matched. Finally, this is month 20, and we see the similar behavior as in month 18. The stronger material at the east side of the polygon seems to play a role in reducing the degradation. The early stages of mining allowed noticing a significant change in the model response before and after the cave breakthrough, which occurred between months 10 and 12. Notice in particular the sudden change in the mild category, which drops from 75% of the drifts to around 30%. It can be noticed that pillar damage is concentrated near the east abutment. For the late stages, and particularly for month 20, all damage categories agree up to 1%. This agreement is a consequence of the best fit that was used to define the S-loss intervals, which only consider the month 20 results. In this slide, we summarize the evolution of rock mass pillar categories in time. Recall that the modeling was implemented without any tunnel support. In hindsight, including some support for example as an equivalent internal pressure, could have helped in differentiating more the severe and moderate categories. Notice, however, that the moderate category still represents a strongly loaded condition for the support. Regardless of the conservative representation of severe damage, it is remarkable that the S-loss range definition allowed a very good agreement for the mild category throughout the entire observational period. So to start wrapping up this presentation, here are some final comments. It is the opinion of the team that was working on this project that the model was able to capture the rock mass damage due to the abutment stresses. Some of the collapses occurring in the west side of the polygon were likely linked to other causes, and not necessarily to the abutment stresses, but rather to the irregular drawing, for example, that occurred. The design for the central macroblock turned out to be quite aggressive. An extensive discussion was provided in Vasquez et al. 2023 about lessons that the corporation learned about this behavior. Some of those considerations and implementations for subsequent macroblocks were increasing the pillar size, reducing the mining front, and implementing ductile support. The calibrated model that we have shown was the foundation for some other modeling carried out for other macroblocks, and some of them are currently in production. Key for the results was an adequate characterization of the rock mass, and that becomes a challenge because the Chuquicamata deposit is well known for heterogeneous rock mass behavior. So that's what we wanted to share with you today. We hope you found it interesting, and we will be happy to answer any questions you may have from this point on. Thank you very much.
So, Catalina, the question is in a few parts. I'll just read out the question, but you should also be able to see it in the Q&A dialogue. To clarify, was a self-propagating caving model generated, or were there geometries imposed manually?
Okay, no, as it was imposed manually with the rate of propagation. This was known. The mine provided the rate, and it was 1:8 for the central macro block. That was the understanding, and so this was imposed, and the cave geometry was built using that rate. It could have been done by a self-propagating algorithm, but it's just because of the model size, it takes much longer, and I think it's enough because what you want to get from the model is just a redistribution of stresses. So you get that by imposing the cave geometry, and what is key in this process is resetting the stresses inside the cave and putting residual properties. So by putting zero stresses initially, then you are able to capture the redistribution of stresses and the abutment stress, which is the one causing the damage in real life, and in this case in the model.
Great, thank you. And I suppose, Catalina, if you had wanted to model the flow numerically, you would have used something like mass flow, which is our caving software.
Yeah, I mean, this took place in 2018 was the first model. Then we did this calibration in 2020-21. And for a couple of years, our office in Santiago is using gravitational flow to capture caving. Yes, so we would have used a couple. That is what we are doing now in our office. But again, Dave, I think it's important that this sort of analysis that are detail-oriented still is better to get the cave geometry from, let's say, a caving model, and then put it in this detail model, because these are very slow models. You have zone size of 40 centimeters. So we try to decouple, because in the caving analysis, you use larger zones. Those are quicker. So we complement both.
Great, thank you. That's definitely a very finely zoned model. Awesome.
Mm-hmm.
The second part of that question, in the case that a self-propagating model was developed, which I guess it wasn't, was a separate stability model created, or was the assessment carried out using the same model?
I think I will just repeat what I just said. We in this case we had a self-propagating model. As I said, those models usually have some size around 10 meters. As this detailed model have half a meter. So we do this sort of self-propagating analysis in independent models. In this case, I will say it, we did this self-propagating analysis before the operation started, and this self-propagating model was able to capture the connection time, that it was around 10 months after the production. And the detailed model, again, since this fine zoning is done independent, okay, because of the running time, you want to optimize it, you want to make sensitivity, so it's never good to have a model that take too long in running times.
Right. Okay, thank you. And then the third part of that question was, when analyzing pillar stability, the evaluation is often done using the S-loss parameter. While this is correlated with field information, what is your opinion on working with pillars that have already yielded, i.e. fully plastified pillars?
Yeah, I think in this case, this is a squat pillar, so it's very hard to analyze these pillars just in terms of yielding or not. So what is done for these squat pillars, you just look at the boundary of the pillar, how much because the core of the pillar may be holding there, but I mean, that is not relevant if your drift is already closed or you have very high convergences. So in this case, it's rather than study the pillar by itself, what you look at it, you look at the convergency of the drift. Because as I said, the core of the pillar, may be fine, but the convergency is already too large. And one thing that you need to keep in mind, that in this layout, some of the pillars may be failing, let's say, but then you have other pillars that may take in that load. So it wouldn't mean necessarily if you have a pillar that is not taking load, that you have a failure there, because you have the other pillars where this load will be redistributed. So as I said, the core of the pillar may be still holding some stresses, but if the outer part of the pillar that has to do with the faces of the drift collapse, then of course you have a stability issue in the infrastructure. I don't know if with that I answer, or I could provide more details.
No, I think that's great. Thank you. Although if the person has a follow-up question, please feel free to do so. So we have a few other questions. How did you obtain residual properties?
Okay. So in this strain softening model that we have, the residual properties, so you have the peak properties, and then the residual properties are defined by default because they follow some relationship, some sort of empirical relationship related to porosity. So the first residual property it will be this post-peak is assuming a model that have zero porosity, but where all the rock briquettes are broken. So it's ready, like all the blocks are ready to start moving. The process of bulking will start, this means that the second residual you get there because of this volumetric strain, and both residuals are, as I said, defined from sort of empirical charts, where the last one you have, with respect to the numerical model, you have some flexibility given by defining the internal residual friction, which by default is 30 degrees. But even though I said that, as it was mentioned during the presentation, what is critical to assess the amount of damage is how fast it goes from peak to post-peak, and that has to do with how brittle or how ductile the rock mass is going to behave. So let's say this relationship where you are saying, okay, with this amount of plastic deformation, you are going to end up with this, say, this first residual, that is the key parameter to making the calibration. If you make it too brittle, then it will just fail almost immediately with little deformation. It will get to lowest strength. If you make it too ductile, then you could say, okay, it's loading, but still it's not causing enough deformation. The degradation of the rock mass is not so fast. And that is the parameter that was used for the calibration, is this sort of critical strain. But then the other parameters that will be this, the only parameter left concerning the post-peak will be this residual internal friction that we could maybe increase it a bit, 35 or 25, and then see sensitivities. But that was not enough. I mean, was not needed, sorry, during this process. Okay?
Great, thank you. Next question. What is the relationship between seismicity, event rate, and S-loss?
Oh, no, they're not. I mean, there is not this straightforward relationship. S-loss is just it's just a measure of you can look at it and how far is the rock mass from the peak to the, let's say, post-peak residual. S-loss is a measure of plasticity, it's a measure of yielding. Seismicity is usually evaluated from elastic models. I mean, it's hard to do it. I mean, there are different ways, or you can evaluate it, I guess, in fault through plastic strain, but in principle, they are not related with seismicity. And S-loss, I just want to stress that S-loss is a parameter, it's like a strength loss. It helps to understand the calibration, but is what is easier to measure or to understand is always a strain deformation. Okay, just S-loss was like a mechanism that helped to correlate the damage in this case. If let's say that we have a perfect situation where we have enough instrumentation with convergency, for instance, then we will always try to look at the strains. I think strains are the most mechanical, intuitive parameters to look at. S-loss is help you to make this sort of correlation, but it's not universal, that you cannot take these numbers from this calibration and use it in any model. Okay?
Great, thank you, and thanks for clarifying that. I might just make a note that in the subscription version of FLAC 3D9, we have added the ability to capture plastic strain tensors, and we're able in IMASS, which is a new software product, to use those to represent the synthetic microseismicity from the model. We had a comment, great presentation. And then the next question is, how were the faults modeled? How many zones across the faults? And also, what was the zone size? Okay, the faults they don't have dimensions. They are implemented with at that time the elements that are known as interfaces. They are discontinuities. So you have for those familiar, is you can slide along. You can have a sliding along these discontinuities. We don't recommend using zones for fault. They are not able to capture properly
the sliding on these discontinuities. So they have no thickness. It's just as I said, they are in Flag 3D. In the latest versions, you have these zone joints elements that are, for those familiar with 3DEX, are very similar to how discontinuities are treated in 3DEX. So we have that capacity in Flag 3D for a while, and it's very important to implement them. It takes an effort because the mesh is harder to build, but certainly these days you cannot use zones. I mean, with what you have in the market now, you cannot use zones to implement faults. You will need at least 4 zones along a fault. If you have 20 faults or 30 faults or more, I mean, it's not possible, and there is not detachment. From a continuous model, you cannot manage detachments as you do in this discontinuous element given by these interfaces or zone joints. So I think it's a good question, so that you please keep in mind that you should really use this continuum element for structures, and that is what we did at that time.
Great, thank you. And I guess I would just add that since this project had been conducted, ITASCA has added what we call zone joints to FLAC 3D. And zone joints are similar to the interfaces that Catalina was mentioning, but they behave more like 3DEC true joints with contact models. They are, I believe, faster, but then they are also work really well where we get many joints or faults intersecting and behave better than we were finding with interfaces. So that's a new development in version 9. Next question. Which other parameters were used as an input aside from the geometry to represent the cave behavior, like S-loss, zone relaxing, stresses, strength reduction, etc.?
Oh, okay. So what you do in this model when you impose the cave, you have the cave geometry. This was done in monthly advances. And then what is key is that in the cave, so initially in your model, you have in situ rock, right? So what you do when you put in the sector where you have the cave geometry, there are 2 crucial things that you should do when modeling. One is to set to 0 the stresses inside the cave. This is very important because this is the mechanism that will help you to cause the redistribution of the stresses around the cave and will be the one causing you the development of the abutment in front of the cave. And as it's broken material, you need to replace the strength of the material that was there in your model by residual properties of the rock mass. I mean, like simulating a broken rock. So these are the 2 things that you need to do to simulate the advance of caving, and then of course you iterate. And when you iterate, you need the model to you need to give a significant number of steps so that it reaches the equilibrium again. And through these 2 activities, that is zeroing the stresses and reducing the strength of the material inside the cave, you will have the redistribution of the stresses, and this is what is going to impact the rock mass that is around the cave, the abutment stresses. Once the cave went through the macro block, then you have what is named the shadow stresses, and those stresses represent a more favorable condition for the drift. Okay?
Great. Let's see, we have one last question. Did the model consider anisotropic, such as ubiquitous joint components on zones, or was it isotropic?
There is one sector. This is that Pato mentioned as this American fault zone. That is like a sector towards the east, where we use an anisotropy because it was known to have a weakness, a known weakness given by the direction of some fault. So yes, we put anisotropy in some sectors. Yeah, not I would say not the main unit, that is this Q equal to S, that is the dominant unit that was isotropic. But we use it. IMASS has the option to include an anisotropy.
Great. And sorry, I lied. Just as I said last question, one last question was posted. 2 parts. Considering the results for convergency and production drifts, 1, other S loss values were evaluated to better adjust the damage model to the damage records. A calibration process was realized. Sorry, would you like me to read that again?
Yeah, I'm not so sure I got the question. I mean, we use S loss. S loss, as I said, it quantifies the strength loss of the rock mass. Okay, so what we use as a calibration was defining these ranges. Which is the range? I mean, if S loss goes from 1 to 0, and in 0 it reaches the post peak, as I said before, when all these rock bridges had broken, then we need to say, so what we relate to moderate damage, what we relate to severe damage. So as part of the calibration was to define these intervals. So when we said between 0, or let's say less than 0.35, it will be severe. Between, I forgot the middle, the moderate range, let's say 0.7 to 0.35 is moderate. This was a calibration. This was like finding a best fit for the errors. Okay, so I mean, we use the range of S loss to calibrate it, or let's say to correlate it to the different degrees of damage. Not so sure if that answered the question.
Okay, thank you. The second part of that question was model damage and drift damage were compared just at the macro block scale and not the drift scale.
Okay, the damage was compared at the drift scale. It's just we didn't just look at the face of the drift. And we look also at depth, not to just consider one value to relate it to damage. So we wanted to take a sort of average. So what we did, we look at the drift scale and we count the places at the drift scale where we were, in which category we were. So it was a local model, but then when and during the presentation, Pato showed this comparison by drift and then a comparison by the whole macro block. But then when we find this sort of ranges for the S loss, yeah, we look at the whole macro block. And then, so in what I'm trying to say, that the model was not expected that we were going to exactly get the right damage at every, let's say, every sector of the drift. I mean, it's a model, it's an homogeneous material. What we wanted is like to, in the overall case, we will have a good representation. So the sort of calibration with this S loss and damage was done at the macro block level. That's correct. But we were always looking at at every sector, I mean, at every segment of the drift. But yeah, we were not trying to exactly, try to match what was happening. As you saw during the presentation, there were some collapse taking place during at the shadow stress condition, which of course this is a model stress strain, so there is no way we can reproduce that. Yeah, so also I'm not so sure if I answered the question.
I think so. Thank you.
Okay.
So sorry, the very, very last one.
Is it true?
Depends how fast I can read the question. Okay, so the inclusion of geological faults could reduce the zones modeled with hexahedral zones. Given this, would it be expected that FLAC3D's capabilities in terms of mixed discretization might be diminished?
Not so sure I am getting the question.
Well, so I would presume you modeled this with a hybrid method where we have more tetrahedral zones right along the faults, and then after that, outside of that, it's presumably hex dominant or a pure hex model.
Yeah.
So correct. I think what they're asking is if the addition of those tetrahedral zones are close to the faults might diminish the results with respect to mixed discretization.
Oh, the tetrahedral zone, yes, it's not something that you want to have in your models, but in this case, you adjust the post-peak behavior so that with less movement, you get the same type of degradation that you will get in some EXA, so that you are able to moderate. Also keep in mind that in FLAC3D, you have this split command for tetrahedras. So the split command will change your tetra elements to hexahedras, so that you can also play with that. Yeah, and yes, I mean, you need to try to have as few tetras as possible. But as I said, in this post-peak behavior, we take into account that they are more rigid than the hexahedras. So I think we have that under control.
Great. Well, thank you very much for all your answers, Catalina. There are no more questions, so I think we'll wrap up. Thanks to Pato for the presentation, and to both of you for an impressive case study and project. So thank you. Thank you, everybody. Mm-hmm. Thank you, everybody, for attending. We will send out a link to this webinar recording if you'd like to follow it up afterwards or watch it afterwards. Let us know if you have any questions or are interested in a free software trial. We have added links to the chat. All right, and with that, thank you and have a good day. Bye-bye.